Today we're going to start learning about trig identities and we'll finish them tomorrow. So before we start, we need to get used to factoring with trig functions and adding and subtracting with trig functions. So some basic stuff to warm up with. To start with, we're going to look at simplifying trig fractions by factoring. Number one is sine of theta squared minus 1 divided by tan of theta times sine of theta minus tangent of theta. So before I factor anything here, let's just recall that you can replace your trig values with a variable if you want to. So the numerator of this fraction we could replace with x squared minus 1. And at that point, you think to yourself, what two factors multiply to -1 and add to 0? And this would factor to x plus 1 times x minus 1. So the same thing goes for the numerator of the actual fraction. We are going to factor this numerator to sine of theta plus 1 multiplied by sine of theta minus 1. For the denominator, you could convert this to variables. You could use, say, y for tangent and x for sine, and then hopefully you recognize that you have a GCF, or you can recognize that each factor already has a value of tangent, so we can use tangent as a GCF. When I take out tangent of theta as a GCF, left over would be sine of theta minus 1. So within each of these factors, I just divided out tangent, and I'm left with sine of theta minus 1. From here, you need to recognize that you have a common factor of sine of theta minus 1. So we can eliminate that common factor. Leaving us with our final simplified answer of sine theta plus 1 in the numerator divided by tangent of theta in the denominator. Before I start number 2, I actually made a typo. It should be the denominator of sine theta times cosine theta plus sine of theta. I'm going to rewrite the whole problem so we can look at this as one whole piece. Our numerator is cosine of theta squared minus 1 divided by the new denominator, or the corrected denominator, of sine theta times cosine theta plus sine theta. All right, and follow along as I go through this. For numbers 3 and 4, we need to simplify by combining fractions. When you're combining fractions, you need to create a common denominator and then add your numerators together. Before we start number 3, I want to bring back some prior knowledge. It's something we haven't talked about in a few classes. So cotangent of theta. Cotangent of theta is equal to x over y. And when we're dealing with the unit circle and trig values, your x value is your cosine value, and your y value is your sine value. So cotangent of theta is equal to cosine of theta divided by sine of theta. This is something we've previously learned. However, it is a trig identity, and we'll be talking about it this class. You do need it in this first problem. Okay, so now that we know that, we're going to look at these two fractions. We have 1 plus sine of theta divided by sine of theta, plus the fraction of cotangent theta minus sine theta divided by cosine of theta. So these denominators don't have anything in common. What we're going to have to do is multiply the first fraction by the second denominator. I'm going to multiply both the numerator and the denominator by cosine of theta. And for the second fraction, I'm going to have to multiply the numerator and the denominator by the denominator of the first fraction. I'm going to need to write these in standard form for the numerators so I can add my terms together. To write them in standard form, that would require me to multiply or distribute my value within the numerator. Starting with the first fraction, I have to distribute cosine of theta to 1 and cosine of theta to sine of theta. That's going to give me a new numerator of cosine theta plus sine theta times cosine theta. And this is divided by our common denominator of sine theta times cosine theta. For the second fraction, you're going to have to do the same thing. Distribute your sine value to both terms in the numerator, giving you a new numerator of cotangent theta times sine theta minus sine theta times cosine theta. And this is divided by the common denominator of sine theta times cosine theta. For the next step, I'm going to add my numerators together, and you can add any like terms, so anything that's exactly the same. If I look at this, I have cosine theta plus sine times cosine theta plus cotangent times sine theta minus sine times cosine theta. So right here we're adding sine and cosine, and here we're subtracting it. So we can actually eliminate both of those terms. So our new numerator, when we add them together, is going to be cosine of theta plus cotangent of theta times sine of theta divided by sine of theta times cosine theta. Now, if you look at this problem, we have all sine and cosine values except for this one cotangent value. And that's where that little memo is I talked about when we first started. Cotangent is equivalent to cosine over sine. So I'm going to replace cotangent with cosine over sine. Rewriting my whole numerator, I have cosine theta plus cosine theta divided by sine theta times sine theta. Technically, sine theta would be over 1 if you want to write it out as a fraction, but I don't need to write that. I think we all know about fractions at this point. Divided by sine theta times cosine theta. Now I can eliminate my value of sine, and I am left with cosine theta plus cosine theta divided by sine theta times cosine theta. In the numerator, if you have two of the exact same factors, which we do, if we had x plus x, we would rewrite that as 2x. So I'm going to rewrite this as 2 times cosine of theta divided by sine of theta times cosine theta. And at this point, we have all multiplication. Our numerator is 2 times cosine. Our denominator is sine times cosine. So we can eliminate that value of cosine of theta, leaving us with our final answer of 2 over sine of theta. Okay, I know these problems are very long when you go through them. We're not going to be doing many of these with today's lesson. This kind of leads into the actual trig identities. So we'll be doing more of these as a warm-up next class as well. But for now, follow along as I go over number 2. It is the same type of problem as number 3, sorry, 3 and 4. It's probably a little bit easier because it's all sine and cosine values. You do not have that tangent value in there. Okay, so like I mentioned, everything in this warm-up box is warming us up to the real trig identities. Today's actual lesson won't have anything quite as involved as this. We'll do more of them next class, which next lesson is this involved, if not more involved. Anyways, moving on to what the trig identities are. Right here, I just have a little note for you. It says two functions, f and g, are said to be identically equal if f of x is equal to g of x, and vice versa. You can obviously switch those. So for every value of x for which both functions are defined, such an equation is referred to as an identity. An equation that is not an identity is called a conditional equation. So we will be working with identities, and if by chance we cannot prove that it's an identity, then we would say it's a conditional equation. But for today, we're going to briefly talk about the identities. They are a lot to learn, so we'll talk about what they are, we'll talk about how to work with them, and then next class we actually prove the identities. So there's three different categories of identities. We have the quotient identities, which are two identities you've already used this year. The first one being tangent is equal to sine over cosine. When we first learned this, we learned that tangent was y over x. But as we learned more about trig values, we learned that the y value is the sine value and the x value is the cosine value. We've also learned that cotangent is cosine over sine, which we started by learning that it was x over y. Besides from the quotient identity, we have what we call the reciprocal identities. We have also talked about these, but we have referred to these as variables as well. These go either way. So we either can say that cosecant of theta is equal to 1 over sine of theta, or you could switch this and say that 1 over sine of theta is equal to cosecant of theta. So you will be using this sometimes, and other times you will be using this. It's probably a good idea to write on your note sheet that you can use it the other way. So let's neatly write that 1 over sine of theta is also equal to cosecant of theta. And you'll be using either one. When we first learned this, we learned that cosecant was 1 over y. Next, we have secant of theta, which is 1 over cosine. And just like the previous one, we could also say 1 over cosine of theta is equal to secant of theta. When we first learned this, we learned that it was 1 over x. And lastly, which we have multiples to talk about with this one, but we know that cotangent of theta is equal to 1 over tangent of theta. Sorry, I'm writing the same thing. We could also say that 1 over tangent of theta is equal to cotangent of theta. You could rework this so many times because you also know that cotangent is going to be cosine over sine. You know that tangent is sine over cosine. So within this one, there's so many more identities that we're going to be working with, but these are the two main ones. So whichever direction you use them in, those are your main identities. And the last set of identities is called Pythagorean identities. And Pythagorean identities come from the Pythagorean theorem, which says that x squared plus, actually, when you learned it, you probably learned it as a. So I'll use that. A squared plus b squared is equal to c squared. This is the same thing. If we look at the first Pythagorean identity, we have sine squared plus cosine squared is equal to 1, or you could say 1 squared, but 1 squared is 1, so we just say is equal to 1. Now, Pythagorean identities, there's three main identities. You see them right here. But within each one of them, you can rework the terms to give you two more identities. And we're going to actually list all of the possibilities right here. So the first one, which is sine squared theta plus cosine squared theta, is equal to 1. To rework this, we could also, let's say, swap the cosine value to the opposite side. So we could subtract cosine squared theta to both sides. That gives us sine of theta squared is equal to 1 minus cosine of theta squared. So same identity in a different form. Besides from that form, we could also subtract sine from both sides so that cosine is by itself. And that gives us the identity of cosine is equal to 1 minus sine of theta squared. So this one identity gives us two more identities, just rearranging the terms. The next identity, we have tangent squared theta plus 1 is equal to secant squared theta. To rearrange these terms, we could start by subtracting 1 from both sides, and that gives us a new identity that says tangent is equal to secant squared minus 1. Or we could subtract tangent from both sides. And we could say that 1 is equal to secant squared minus tangent squared. So our one identity just gave us two more. And the last Pythagorean identity is cotangent squared plus 1 is equal to cosecant squared. And we're going to do the same thing here. If we rearrange these terms, we could have cotangent squared is equal to cosecant squared minus 1. Or we could have 1 is equal to cosecant squared minus cotangent squared. So the reason why I'm going over all of these is because these are all of the Pythagorean identities. We actually see 9 of them right here. But in previous years, students have had to memorize the Pythagorean identities. So if you memorize the original 3 and you write those down on your paper, like say a quiz or a test, you could then just rework them to find the other 6. So that's why I only listed those 3. There are multiples. Obviously, there's all of these ones that I just listed. Okay, so the only examples that we're going to go over today is kind of working us into getting used to what the identities are and how to replace things with its identity. Next class, we will be proving things that equal each other. For now, let's take a look at example 1. Example 1 is cotangent of theta divided by cosecant of theta. And when you simplify these, you should end up with one term when you're done. So I'm looking at cotangent and I'm looking at cosecant. The only thing I can do for number 1 is I'm going to use my highlighter, my purple highlighter. Cotangent, I'm going to replace with cosine over sine. And then I'm going to replace cosecant with 1 over sine. I have one quotient identity in my numerator, one reciprocal identity in my denominator. So I can rewrite this as cosine of theta divided by sine of theta all over 1 divided by sine of theta. And when you're dividing by a fraction, you can multiply by its reciprocal. So we end up with cosine of theta divided by sine of theta multiplied by sine of theta divided by 1. And you can eliminate your sine of theta value, leaving you with your single solution of cosine theta. Number 2, we have tangent of theta multiplied by cosecant of theta minus sine of theta. So we have quite a few things happening within this one. I'm going to replace all of them with their identity, starting with tangent, which I'm going to replace with sine of theta divided by cosine of theta. Now, before I move any further, some of you might be wondering why I'm not using this identity right here. So the reason why I'm not using that identity for cotangent or for tangent at this point is because everything else in my trig equation can be converted to sine or cosine. So if you can do that, make everything sine or cosine, and then eliminate whichever one you can. That's going to be the easiest way to simplify these. That's why I choose to convert tangent to sine over cosine instead of 1 over cotangent. Okay, so tangent converted to sine over cosine. Cosecant is going to convert to 1 over sine. And then I have minus sine of theta. All right, so in the second part, we're going to pull a little bit of this from our warm-up. We are subtracting trig values here. So what I'm going to do is I'm going to create a single fraction. Technically, my second fraction is over 1, and I'm going to multiply the top and bottom of this fraction by sine of theta. This is going to give me sine of theta divided by cosine of theta multiplied by 1 over sine theta minus sine squared theta, because we're multiplying 2 of them, divided by sine of theta. Now, inside of my parentheses, I can simplify this to one single fraction, giving me sine of theta divided by cosine of theta multiplied by 1 minus sine squared theta divided by sine of theta. This is multiplication, so I see that I can eliminate sine of theta in my numerator and in my denominator. And now I should be left with one value. So if I scroll out and I look up here at my identities, when we reworked our Pythagorean identities, I was thinking about what I was trying to say here. We reworked this one. Let's use pink. We reworked 1 minus sine squared, and we set it equal to cosine of squared. So notice this is what we're dealing with. We're dealing with 1 minus sine squared. I'm going to replace that with cosine squared. And the reason why I'm going to do that, the reason why it benefits me, is because my denominator is also cosine. So that leaves me with cosine squared divided by cosine. And if I have two values of cosine in the numerator, I can eliminate one of those values, and I can eliminate one of those in the denominator. And this leaves me with my final answer after all of that work with just cosine of theta. And that's my final answer. Okay, so I'm gonna work on the on your own section. If you guys want to follow along as I go through it, feel free. If you want to get started on your practice, you can. Please let me know if you have any questions about the identities. It's definitely helpful when you're working through these. Again, we're just doing basic ones today, but it's helpful to have these charts in front of you so that you know everything you can replace your original expression with. I also always make the suggestion to get every term to sine and cosine if possible. That's going to usually make it easier. Of course, there's a few cases where that won't happen, but generally creating all sine and cosine values will eliminate your expressions faster. Also, one last note before I switch over and just work on the on your own section. There's multiple ways to arrive at the same answer for trig identities. You may have done these problems different than me, but you end up with the same answer, and that's completely okay. There's countless identities to choose from. So you might be able to rework the same problem with a different identity and get the same answer. Okay, so for the on your own section,